Alright, so hello everyone. Today I don't have a good topic for what we're covering today because it's just the appendix to this chapter we've been working on so far. Just in order to get more acquainted with more extreme pathological cases, I think is the main goal here. Also, I'm sorry, there's going to be a lot more background noise in this one than there is usually. There's all sorts of ventilation here going off now, so we'll have to deal with that. But our first topic here is on a non-regular Hausdorff manifold. So this is an example we're constructing of a Hausdorff manifold over an ultrametric field which has a point which does not have a fundamental system of open and closed neighborhoods. This is said to be by George Bergman. So let K be a complete ultrametric field with a valuation ring of A. Suppose we can find an X in A which is non-zero, such that A over X times A is infinite. And then we contend that A is analytically isomorphic to A without zero. And we show this by showing that A and A minus 0 may both be represented as the disjoint union of the same number, an equal number of cardinal copies of A. First, we note if mu is a positive integer, then the cosets of x to the mu times A are isomorphic to A. And we note that A is the disjoint union of the cosets of x times alpha, while A minus 0 is the disjoint union of the following collection of cosets of x to the mu alpha with mu ranging over the positive integers. First off, we have the cosets of x times a, accepting x times a. We have the cosets of x squared a in xa, accepting x squared a, and so on. I'm going to actually probably should be indexing these with numbers. So it's 1 to 2 up to our mu, which is the cosets of x to the mu of alpha in x to the mu minus 1 alpha, accepting x mu to the alpha. Now, since a over xa is infinite, both sets of cosets have the same cardinality. We may view this as smoothly attaching a point P to the ball A, where A is then inside of the union of A and P, which is then isomorphic to A, with P as 0 in the latter. And this attaching has 3 important properties. First off, the intersection of A and P is a Hausdorff analytic manifold. Second, P is in the closure of A, and third, P is not in the closure of any coset of the maximal ideal of A. And this is a property of the fact, consequence of the fact that 0 is far away from any of the cosets we use to describe A minus 0. Now we repeat this process countable times. So we can attach P0 through P mu to alpha through x to mu times alpha. And then we're going to attach another point P to the mu plus 1 to x to the mu plus 1 alpha, and pass this to the limit. And give this limit the topology such that each x and p0 through p mu is open with its original topology. And since these points are all far away, we see that x is Hausdorff, x as the limit is Hausdorff. Where the point 0 and A has no fundamental system of neighborhoods which are open and closed. You see the powers of x to mu alpha are a fundamental system of neighborhoods of 0. And it's glitching. If we had a fundamental system of neighborhoods of 0 which were open and closed, not write the word closed, we could find one such neighborhood U contained in A. But then the closure of x to the mu alpha in U must contain Pu, which is not alpha, which is a contradiction. Alright, and that's our proof that our manifold is as desired. One thing to note here, though, is that our original specification that we found a point in the evaluation ring non-zero where the quotient is infinite is not necessarily an obvious one to satisfy. And we can verify that there exists x in A such that x is not 0 and x over ax is infinite if and only if one of the following is satisfied. First off, the residue field of our base ultrametric field K must be infinite, or the valuation on K takes on non-discrete set of values. And the only ultrametric fields not meeting one of these conditions are the finite extensions of the p-adics and the fields, this is the formal power series over a finite field. Alright, and so that's kind of our first example to note there. Next up, we're going to be looking at the structure of p-adic manifolds. Kind of an important thing to get our head around potentially. So we're going to use, it says here, we're going to use the notion of disjoint union to study manifolds when K is locally compact and ultrametric as the p-adics are. We're going to do a bit of setup where we're going to pick an integer n, which is going to be non-negative, and we assume that x is everywhere of dimension m. And we're going to assume that x is Hausdorff and non-empty. Otherwise, it's going to be pretty boring. And this brings us to our first lemma. So let R be a positive real number and x be in k to the n. Then the ball of radius r around x is compact and open, which will of course make every ball in X as being compact and open. Alright, and let's look at the proof. First off, we need compactness. Since our base field is locally compact, there exists a positive real number epsilon greater than 0 such that any ball of radius s less than epsilon times r about x in k to the n is contained in a compact neighborhood of X. Since these balls are closed in K to the n, they are compact. These balls. Now, since the absolute value on K is non-trivial, we can choose a non-zero alpha in K with an absolute value less than epsilon. And then the transformation f of y actually, be equal to x plus alpha times y minus x is a topological isomorphism of the ball of radius r about our x, that's where the x comes from, onto the ball whose radius is scaled by alpha and is still around x, of course. So b of r of x is compact. Now, we also need openness. So we can contend that if y is in the ball of radius r about x, then I've seen this before. This is a cool fact actually. Then the ball of radius r about y is actually the same as the ball of radius r about x. So every point in a ball is technically it's centered in this ultrametric space. So b of r of x is a neighborhood of y. Now, since x is obviously going to be in the ball of radius r around y, we can just show that the ball of radius y is inside of the ball of radius x by symmetry, and then the symmetry will give equality. So then for z in the ball of radius r about y, the distance between z and x is by our ultrametric inequality. At most, the distance between z and y, the distance between y and x, which is less than or equal to r, since z is in the ball around y and y is in the ball around x. So our point, which is arbitrary in the ball around y, is in the ball radius r around x. And here we have the ultrametric inequality, of course. Essentially we have x and y. X is within a ball of radius r around y, and y is in a ball of radius r around x. The idea if x is distance to z to x has to be smaller than one of these, so this point here has to be in both either way. That diagram is actually kind of not helpful, but whatever. And we also see if we have bi being balls of radius ri with R1 being at most R2, then B1 is inside or disjoint of is, let's use from inside or just inside of or disjoint from B2. And this kind of all ties back to that bad diagram of p-adic space I drew earlier. These are all known properties of p-adic space. Which brings me to my second lemma. Let U be a closed and open set of a ball B in U in K to the N. There is a positive radius R smaller than the radius of B, such that U is the disjoint union of a finite number of balls of radius R. Let's look at our proof. We're going to let V be the points in our ball not in U. So U and V is an open cover of the compact metric space B. Hence, there is a radius R less than the radius of B, such that, one sec, this is all especially bad, I think. Radius R is smaller than the radius of B, such that for all x in B, the ball of radius R about x in B is contained in U or V. By the preceding remark, you see that a ball radius R in B is a ball of radius R in K to the N. So U is the union of balls of radius R in K to the N. The union is disjoint by our previous remark, and so it must be finite as U is compact. And we see from this, if B is a ball in X, and U being both closed and open in B, U is the disjoint union of finite balls in X. Isn't that just restating the lemma, essentially? I guess with no restriction on the radius, but that's should be easier, right? And this brings us to a theorem, which is another following our equivalent. And our first condition is that X is paracompact, which I'm looking up what that means. That's every open cover has a locally finite open refinement. That is equivalent to saying in this context that X is the disjoint union of balls. And proof, of course, 2 implying 1 is trivial, so we're going to look at 1 implying 2. We first want to note X has a locally finite covering. By balls. So we know X has a covering by balls. Say U to the L, U to the lambda for lambda in L. And choose a locally finite open refinement V mu for mu in M, why not, of this, and then of our collection of, I'll write as our collection of views, and then a locally finite closed refinement of W across nu for nu in N of this collection of V's. Let phi be from M to L and C from N to M, such that v of mu, v of nu, each v of nu is in U of v of nu, and that each W of nu is in V of C of nu. We're going to let nu be in N. Then Okay, this chapter goes on forever, so... Alright, then we have that W of nu is contained in V of C of nu contained in U of V of C of nu. Now, since W of nu is closed and U of V of C of nu is compact, we know that W of nu must be compact. Then, since V of C of nu is open, we may cover W of nu by a finite number of balls B nu comma I, for I being an indexing set and self-indexed by nu, such that B of nu and I is contained within V of C of V for all I. Then the covering B consisting of V and I consists of balls and is locally finite. Since any ball Vi meets at most finitely many V moves, and hence only finitely many B V primes I primes for whatever that must be, V being nu, because I misspoke. And we're now going to write UI as the locally finite covering of X by balls which we have attained above. Then each UI is open and compact, and meets finitely many U sub j's. So we're going to let f of I denote the finite subsets of I. Then for j being an f of I, I'm going to define U of j to be the union over I in j of ui, that's intersection, not union, with itself intersected with the elements of x not in any uj for j not in j. Note that x minus the union of our uj is open and compact. If j is empty, this is trivial. If I is in J, this is the finite intersection. This set here is a finite intersection of open and compact sets comprising of the union for J not equal to J of Ui minus Uj where J is such that Uj intersected with Ui is non-zero. Hence that whenever Uj is non-empty, then it is an open, compact subset of a ball hence is a finite union of balls. Note that by definition, the U over J's in our f of I are disjoint. So we are done by the covering U sub J, and we are going to finish it here. This is not the end of our section, but we have like how long do we have? So we've done 1, 2, 3 pages. That's 1.5. Just gonna be half our time. Yeah, that's gonna put us over time. So I'm just gonna end it here. Kind of an awkward place for next time, but that's how it goes sometimes. I mean, there's a lot of background noise in this one anyway, so I don't want to record too much. But yeah, thanks for watching. Thanks for putting up with this. Join me next time, I guess.